In this problem, we have an observer. She is 300 meters from the launch pad of a rocket, and she's watching it ascend vertically at a rate of 60 meters per second. We're asked to find the rate of change of the distance between the rocket and the observer when the rocket's 400 meters high. So our cube approach says let's circle our numbers and variables if they're here. In this case, we just have numbers. So we've got right, that the observer is 300 meters, it's ascending at a rate of 60 meters per second, and it is 400 meters high. So we want to, here's the question, we want to find the rate of change of the distance between the rocket and the observer when the rocket is 400 meters high. So here's our question. And then boxing any math expressions. So we've got from the launch pad. So from the launch pad is a distance. So that really is incorporating a mathematical idea. It's going to be, in our case, probably a variable. She watches it ascend vertically at a rate. So this is a calculus expression. Rate is a derivative. And ascending means that it's a positive derivative. And we want to find the rate of change of the distance between the rocket and the observer. So that's a rate of change, another derivative. And extraneous, I guess we could say we don't care that she's watching it. Everything else seems fairly important. Okay, so let's organize our thoughts about this problem. So first off, we have that we have an observer. Right? So let's give ourselves an observer. My great stick figure. She's observing a rocket ascend from a launch pad. So I'll draw my launch pad. And let's draw some rocket. And it's ascending vertically. We know that the distance between the observer and the launch pad is not changing. It's 300 meters. We know the rocket is ascending. So this is its ascension, going up and down, is some variable. So I'll call it y. And we want to know the rate of change of the distance between the rocket and the observer. So we can look at that as a straight line from the observer to the rocket. And I'm measuring, in this case, from the foot of the observer, and we'll call that x. So we've got a nice diagram, at least relating x and y, the rocket, the observer. We've expressed this from the launch pad is 300 meters, ascending vertically. Okay, that's a rate of change. So we need to write that here. Well, first let's remind ourselves, or make sure it's clear. Let's write it down. Y is height of rocket, and x is the distance. So x is distance from observer to rocket. Right, so we've got it here. We know exactly what our variables are. And so the ascension of the rocket, that's going to be dy dt. And we know it's time because it's 60 meters per second. So 60 meters per second. And we're asked, so the last boxed expression is what is the rate of change of the distance? And we've described that as x. So what is dx dt equal to when the distance between the rocket and the observer is 400 meters. So the distance from the rocket and the observer. So when is this? So when is x equal to 400? I'm sorry. Let's read this question a little bit. And this is what happens when I'm trying to write and talk and read all at the same time. Sorry, I'm not the best juggler. So yes, I want to know the rate of change of the distance between the rocket and the observer. So that's the rate of change of x when the rocket is 400 meters. So I wrote when x is equal to 400, but that is not what's being asked. It is when the rocket is 500 meters high. Well, that's why. So I apologize, but this is really good. That we should always be double checking that what we're writing is makes total sense. So we will know dx dt when y is equal to 400. So let me box that because this is the question we want to ask. This will help us make decisions when we're solving the problem. So great, we've organized all of the facts from the problem into variables and different relationships. However, we don't have a relationship yet between x and y, but the picture should be incredibly suggestive that again we have a right triangle. So we know that y squared plus 300 squared is equal to x squared. Right? The sum of the squares of the height and the base is equal to the hypotenuse squared. That's Pythagorean's theorem. So we've related our variables, and now we need to determine an approach, and this is a related rates problem, so our approach will be to use implicit differentiation to solve. So that's what we're going to do. We're going to take this expression here, that y squared plus 300 squared is equal to x squared, and use implicit differentiation to find out a formula for dx dt. So taking the differential of both sides, I take the differential of y squared plus 300 squared, and it is equal to the differential of x squared. Applying our differential rules, this distributes across addition, and I know that the differential, so 2y dy, right? That's the differential of y squared, plus, well, the differential of 300 is 0, so there is no plus anything, and it's equal to the differential of x squared, which is 2x dx. Great. We have done our implicit differentiation, but I don't want to solve for dy dx. Why? Because back here, what do we want to solve for is dy dt. So I divide both sides by dt. So I divide this expression by dt, and I divide this expression by dt, and I get that 2y dy dt is equal to 2x dx dt, and I know something about dy dt. I know that dy dt is equal to 60 meters per second. So I can replace that there. And so this whole expression becomes that 60 times 2 is 120. So 120 y is equal to 2x dx dt or that dx dt is equal to 60y divided by x. So now we have a formula for dx dt, and I want to know what is dx dt when y equals 400. Just like the last problem, my dx dt is in form of two variables, y and x. So I have a side problem. I need to know what is y equal to, so I'll look at this side problem. I want to know what is x equal to when y is equal to 400. And we can come back, we have our relationship to y and x. Y squared plus 300 squared equals x squared. So this tells me that 400 squared plus 300 squared is x squared. So x squared, or x, is equal to plus or minus square root of 400 squared plus 300 squared, which is equal to plus or minus 500. And we get two answers for x, but again, in this problem, the x value cannot be negative because we're talking about distance, so I'm only going to be concerned about the positive value. So x equals 400, and finally solving the problem. Again, I'm going to box this off so we're clear that it's different from everyone else. So the problem is, what is dx dt equal to at the point x is 500, y is 400, and this is equal to 60 times our y value, which is 400, divided by our x value, which is 500, and this is equal to 48. And what are our units? Well, again, our only unit came from dy dt, which was meters per second, so that carries over. This will be meters per second. So if I were to write out the solution for this, and you should write this out, the answer would be that the rate of change of the distance between the rocket and the observer when the rocket is 400 meters high is 400 meters per second.